Vitamin C, Wikipedia article audio. Vitamin C, also known as ascorbic acid and L-ascorbic acid, is a vitamin found in food and used as a dietary supplement. The disease scurvy is prevented and treated with vitamin C containing foods or dietary supplements. Evidence does not support use in the general population for the prevention of the common cold. There is, however, some evidence that regular use may shorten the length of colds. It is unclear if supplementation affects the risk of cancer, cardiovascular disease, or dementia. It may be taken by mouth or by injection. Vitamin C is generally well tolerated. Large doses may cause gastrointestinal discomfort, headache, trouble sleeping, and flushing of the skin. Normal doses are safe during pregnancy. The United States Institute of Medicine recommends against taking large doses. Biology. Significance. Vitamin C is an essential nutrient involved in the repair of tissue and the enzymatic production of certain neurotransmitters. It is required for the functioning of several enzymes and is important for immune system function. It also functions as an antioxidant. Foods containing vitamin C include citrus fruits, broccoli, Brussels sprouts, raw bell peppers, and strawberries. Prolonged storage or cooking may reduce vitamin C content in foods. Vitamin C was discovered in 1912, isolated in 1928, and in 1933 was the first vitamin to be chemically produced. It is on the World Health Organization model list of essential medicines, the most effective and safe medicines needed in a health system. Vitamin C is available as a generic medication and over-the-counter drug. In 2015, the wholesale cost in the developing world was less than $0.01 per tablet. Partly for its discovery, Albert Szent-Györgyi and Walter Norman Hayworth were awarded 1937 Nobel Prizes in Physiology and Medicine and Chemistry, respectively. Vitamin C is an essential nutrient for certain animals including humans. The term vitamin C encompasses several vitamins that have vitamin C activity in animals. Ascorbate salts such as sodium ascorbate and calcium ascorbate are used in some dietary supplements. These release ascorbate upon digestion. Ascorbate and ascorbic acid are both naturally present in the body, since the forms interconvert according to pH. Oxidized forms of the molecule such as dehydroascorbic acid are converted back to ascorbic acid by reducing agents. Vitamin C is a cofactor in at least 8 enzymatic reactions in animals important in many essential functions, including wound healing. In humans, vitamin C deficiency compromises collagen synthesis, contributing to the more severe symptoms of scurvy. More generally, the biochemical role of vitamin C is to act as an antioxidant, a reducing agent, donating electrons to various enzymatic and non-enzymatic reactions. Doing so converts vitamin C to an oxidized state, either as semi-dehydroascorbic acid or dehydroascorbic acid. These compounds can be restored to a reduced state by glutathione and NADPH-dependent enzymatic mechanisms. In plants, vitamin C is a substrate for ascorbate peroxidase. This enzyme utilizes ascorbate to neutralize toxic hydrogen peroxide by converting it to water. Deficiency. Scurvy is an avitaminosis resulting from lack of vitamin C, since without this vitamin, collagen made by the body is too unstable to perform its function. Scurvy leads to the formation of brown spots on the skin, spongy gums, and bleeding from all mucous membranes. The spots are most abundant on the thighs and legs, and a person with the ailment looks pale, feels depressed, and is partially immobilized. In advanced scurvy there are open, suppurating wounds and loss of teeth and, eventually, death. The human body can store only a certain amount of vitamin C, and so the body stores are depleted if fresh supplies are not consumed. The time frame for onset of symptoms of scurvy in unstressed adults on a completely vitamin C-free diet, however, may range from 1 month to more than 6 months, depending on previous loading of vitamin C. Uses. Notable human dietary studies of experimentally induced scurvy have been conducted on conscientious objectors during World War II in Britain and on Iowa state prisoners in the late 1960s to the 1980s. These studies both found that all obvious symptoms of scurvy previously induced by an experimental scorbutic diet with extremely low vitamin C content could be completely reversed by additional vitamin C supplementation of only 10 mg a day. In these experiments, there was no clinical difference noted between men given 70 mg vitamin C per day and those given 10 mg per day. Men in the prison study developed the first signs of scurvy about 4 weeks after starting the vitamin C-free diet, whereas in the British study, 6 to 8 months were required, possibly due to the preloading of this group with a 70 mg/day supplement for 6 weeks before the scorbutic diet was fed. Men in both studies on a diet devoid, or nearly devoid, of vitamin C had blood levels of vitamin C too low to be accurately measured when they developed signs of scurvy, and in the Iowa study, at this time were estimated to have a body pool of less than 300 mg, with daily turnover of only 2.5 mg/day, implying an instantaneous half-life of 83 days by this time. Vitamin C has a definitive role in treating scurvy, which is a disease caused by vitamin C deficiency. Beyond that, a role for vitamin C as prevention or treatment for various diseases is disputed, with reviews reporting conflicting results. A 2012 Cochrane review reported no effect of vitamin C supplementation on overall mortality. It is on the World Health Organization's list of essential medicines as one of the most effective and safe medicines needed in a health system. Scurvy. The disease scurvy is caused by vitamin C deficiency and can be prevented and treated with vitamin C containing foods or dietary supplements. It takes at least a month of little to no vitamin C before symptoms occur. Early symptoms are malaise and lethargy, progressing to shortness of breath, bone pain, bleeding gums, susceptibility to bruising, poor wound healing, and finally fever, convulsions, and eventual death. Until quite late in the disease the damage is reversible, as with vitamin C repletion, healthy collagen replaces the defective collagen. Treatment can be orally or by intramuscular or intravenous injection. Scurvy was known to Hippocrates in the classical era. The disease was shown to be prevented by citrus fruit in an early controlled trial by a Royal Navy surgeon, James Lind, in 1747, and from 1796 lemon juice was issued to all Royal Navy crewmen. Infection. The effect of vitamin C on the common cold has been extensively researched. The earliest publication of a controlled clinical trial appears to be from 1945. Researchers continued to work on this question, but research interest and public interest spiked after Linus Pauling, two-time awardee of the Nobel Prize, started publishing research on the topic and also published a book, Vitamin C and the Common Cold, in 1970. A revised and expanded edition, Vitamin C, The Common Cold and the Flu was published in 1976. Cancer. A Cochrane review published in 2013 with inclusion criteria limited to trials that called for at least 200 mg/day concluded that vitamin C taken on a regular basis was not effective in prevention of the common cold. Limiting inclusion to trials that called for at least 1000 mg/day made no difference. However, taking vitamin C on a regular basis did reduce average duration by 8% in adults and 14% in children, and also reduced severity of colds. A subset of trials reported that supplementation reduced the incidence of colds by half in marathon runners, skiers, or soldiers in subarctic conditions. Another subset of trials looked at therapeutic use, meaning that vitamin C was not started unless the people started to feel the beginnings of a cold. In these, vitamin C did not impact duration or severity. An earlier review stated that vitamin C did not prevent colds, did reduce duration, did not reduce severity. The authors of the Cochrane review concluded that, given the consistent effect of vitamin C on the duration and severity of colds in the regular supplementation studies, and the low cost and safety, it may be worthwhile for common cold patients to test on an individual basis whether therapeutic vitamin C is beneficial for them. Vitamin C distributes readily in high concentrations into immune cells, has antimicrobial and natural killer cell activities, promotes lymphocyte proliferation, and is consumed quickly during infections, effects indicating a prominent role in immune system regulation. The European Food Safety Authority found a cause and effect relationship exists between the dietary intake of vitamin C and functioning of a normal immune system in adults and in children under 3 years of age. Cardiovascular disease. There are two approaches to the question of whether vitamin C has an impact on cancer. First, within the normal range of dietary intake without additional dietary supplementation, are people who consume more vitamin C at lower risk for developing cancer, and if so, does an orally consumed supplement have the same benefit? Second, for people diagnosed with cancer, will large amounts of ascorbic acid administered intravenously treat the cancer, reduce the adverse effects of other treatments, and so prolong survival and improve quality of life? A 2013 Cochrane review found no evidence that vitamin C supplementation reduces the risk of lung cancer in healthy or high-risk people. A 2014 meta-analysis found that vitamin C intake might protect against lung cancer risk. A second meta-analysis found no effect on the risk of prostate cancer. Two meta-analyses evaluated the effect of vitamin C supplementation on the risk of colorectal cancer. One found a weak association between vitamin C consumption and reduced risk, and the other found no effect of supplementation. A 2011 meta-analysis failed to find support for the prevention of breast cancer with vitamin C supplementation, but a second study concluded that vitamin C may be associated with increased survival in those already diagnosed. Under the rubric of orthomolecular medicine, intravenous vitamin C is a contentious adjunctive cancer therapy, widely used in naturopathic and integrative oncology settings. With oral administration, absorption efficiency decreases as amounts increase. Intravenous administration bypasses this. Doing so makes it possible to achieve plasma concentrations of 5 to 10 millimoles/liter, which far exceed the approximately 0.2 moles/L limit from oral consumption. The theories of mechanism are contradictory. At high tissue concentrations, ascorbic acid is described as acting as a prooxidant, generating hydrogen peroxide to kill tumor cells. The same literature claims that ascorbic acid acts as an antioxidant, thereby reducing the adverse effects of chemotherapy and radiation therapy. Research continues in this field, but a 2014 review concluded, currently, the use of high-dose intravenous vitamin C cannot be recommended outside of a clinical trial. A 2015 review added, there is no high-quality evidence to suggest that ascorbate supplementation in cancer patients either enhances the anti-tumor effects of chemotherapy or reduces its toxicity. Evidence for ascorbate's anti-tumor effects was limited to case reports and observational and uncontrolled studies. A 2013 meta-analysis found no evidence that vitamin C supplementation reduces the risk of myocardial infarction, stroke, cardiovascular mortality, or all-cause mortality. However, a second analysis found an inverse relationship between circulating vitamin C levels or dietary vitamin C and the risk of stroke. A meta-analysis of 44 clinical trials has shown a significant positive effect of vitamin C on endothelial function when taken at doses greater than 500 mg per day. The endothelium is a layer of cells that line the interior surface of blood vessels. Endothelial dysfunction is implicated in many aspects of vascular diseases. The researchers noted that the effect of vitamin C supplementation appeared to be dependent on health status, with stronger effects in those at higher cardiovascular disease risk. Studies examining the effects of vitamin C intake on the risk of Alzheimer's disease have reached conflicting conclusions. Maintaining a healthy dietary intake is probably more important than supplementation for achieving any potential benefit. A 2010 review found no role for vitamin C supplementation in the treatment of rheumatoid arthritis. Vitamin C supplementation does not prevent or slow the progression of age-related cataract. Other diseases. More than 2 to 3 grams may cause indigestion, particularly when taken on an empty stomach. However, taking vitamin C in the form of sodium ascorbate and calcium ascorbate may minimize this effect. Other symptoms reported for large dose include nausea, abdominal cramps, and diarrhea. These effects are attributed to the osmotic effect of unabsorbed vitamin C passing through the intestine. In theory, high vitamin C intake may cause excessive absorption of iron. A summary of reviews of supplementation in healthy subjects did not report this problem, but left as untested the possibility that individuals with hereditary hemochromatosis might be adversely affected. There is a long-standing belief among the mainstream medical community that vitamin C increases risk of kidney stones. Reports of kidney stone formation associated with excess ascorbic acid intake are limited to individuals with renal disease. Reviews state that data from epidemiological studies do not support an association between excess ascorbic acid intake and kidney stone formation in apparently healthy individuals, although one large, multi-year trial did report a nearly twofold increase in kidney stones in men who regularly consumed a vitamin C supplement. Vitamin C is a water-soluble vitamin, with dietary excesses not absorbed, and excesses in the blood rapidly excreted in the urine, so it exhibits remarkably low acute toxicity. Side effects. Recommendations for vitamin C intake by adults have been set by various national agencies. 40 mg per day, India National Institute of Nutrition, Hyderabad, 45 mg per day or 300 mg per week, the World Health Organization, 80 mg per day, the European Commission Council on Nutrition Labeling, 90 mg/day and 75 mg/day. Health Canada 2007, 90 mg/day and 75 mg/day. United States National Academy of Sciences, 100 mg per day. Japan National Institute of Health and Nutrition, 110 mg/day and 95 mg/day. European Food Safety Authority. In 2000, the North American Dietary Reference Intake chapter on vitamin C updated the recommended dietary allowance to 90 mg per day for adult men and 75 mg/day for adult women, and set a tolerable upper intake level for adults of 2000 mg/day. The table shows RDAs for the United States and Canada for children, and for pregnant and lactating women. For the European Union, the EFSA set higher recommendations for adults, and also for children, 20 mg/day for ages 1-3, 30 mg/day for ages 4-6, 45 mg/day for ages 7-10, 70 mg/day for ages 11-14, 100 mg/day for males ages 15-17, 90 mg/day for females ages 15-17. For pregnancy 100 mg/day, for lactation 155 mg/day. India, on the other hand, has set recommendations much lower, 40 mg/day for ages 1 through adult, 60 mg/day for pregnancy, and 80 mg/day for lactation. Clearly, there is not consensus among countries. Cigarette smokers and people exposed to second-hand smoke have lower plasma vitamin C levels than non-smokers. The thinking is that inhalation of smoke causes oxidative damage, depleting this antioxidant vitamin. The U.S. Institute of Medicine estimated that smokers need 35 mg more vitamin C per day than non-smokers, but did not formally establish a higher RDA for smokers. One meta-analysis showed an inverse relationship between vitamin C intake and lung cancer, although it concluded that more research is needed to confirm this observation. 3 enzymes that are required for the hydroxylation of proline and lysine in the synthesis of collagen. These reactions add hydroxyl groups to the amino acids proline or lysine in the collagen molecule via prolyl hydroxylase and lysyl hydroxylase, both requiring vitamin C as a cofactor. Hydroxylation allows the collagen molecule to assume its triple helix structure, and thus vitamin C is essential to the development and maintenance of scar tissue, blood vessels, and cartilage, 2 enzymes that are necessary for synthesis of carnitine. Carnitine is essential for the transport of fatty acids into mitochondria for ADP generation. The remaining 3 enzymes have the following functions in common, alongside their other functions. Dopamine beta-hydroxylase participates in the biosynthesis of norepinephrine from dopamine. Peptidylglycan alpha-amidating monooxygenase amidates peptide hormones by removing the glyoxylate residue from their C-terminal glycan residues. This increases peptide hormone stability and activity. 4-hydroxyphenylpyruvate dioxygenase modulates tyrosine metabolism. The U.S. National Center for Health Statistics conducts biannual National Health and Nutrition Examination Survey to assess the health and nutritional status of adults and children in the United States. Some results are reported as What We Eat in America. The 2013 to 2014 survey reported that for adults ages 20 years and older, men consumed on average 83.3 mg/d and women 75.1 mg/d. This means that half the women and more than half the men are not consuming the RDA for vitamin C. The same survey stated that about 30% of adults reported they consumed a vitamin C dietary supplement or a multivitamin/mineral supplement that included vitamin C, and that for these people total consumption was between 300 and 400 mg/d. Diet. Recommended levels. Food labeling. Sources. In 2000, the Institute of Medicine of the U.S. National Academy of Sciences set a tolerable upper intake level for adults of 2000 mg/day. The amount was chosen because human trials had reported diarrhea and other gastrointestinal disturbances at intakes of greater than 3000 mg/day. This was the lowest observed adverse effect level, meaning that other adverse effects were observed at higher intakes. The European Food Safety Authority reviewed the safety question in 2006 and reached the conclusion that there was not sufficient evidence to set a UL for vitamin C. The Japan National Institute of Health and Nutrition reviewed the same question in 2010 and also reached the conclusion that there was not sufficient evidence to set a UL. For U.S. food and dietary supplement labeling purposes, the amount in a serving is expressed as a % of daily value. For vitamin C labeling purposes, 100% of the daily value was 60 mg, but as of May 27, 2016 it was revised to 90 mg to bring it into agreement with the RDA. A table of the old and new adult daily values is provided at reference daily intake. Food and supplement companies have until January 1, 2020 to comply with the change. European Union regulations require that labels declare energy, protein, fat, saturated fat, carbohydrates, sugars, and salt. Voluntary nutrients may be shown if present in significant amounts. Instead of daily values, amounts are shown as % of reference intakes. For vitamin C, 100% RI was set at 80 mg in 2011. The richest natural sources are fruits and vegetables. Vitamin C is the most widely taken nutritional supplement and is available in a variety of forms, including tablets, drink mixes, and in capsules. Vitamin C is absorbed by the intestines using a sodium ion-dependent channel. It is transported through the intestine via both glucose-sensitive and glucose-insensitive mechanisms. The presence of large quantities of sugar either in the intestines or in the blood can slow absorption. While plants are generally a good source of vitamin C, the amount in foods of plant origin depends on the precise variety of the plant, soil condition, climate where it grew, length of time since it was picked, storage conditions, and method of preparation. The following table is approximate and shows the relative abundance in different raw plant sources. As some plants were analyzed fresh while others were dried, the data are subject to potential variation and difficulties for comparison. The amount is given in milligrams per 100 grams of the edible portion of the fruit or vegetable. Animal-sourced foods do not provide much vitamin C, and what there is destroyed by the heat of cooking. For example, raw chicken liver contains 17.9 mg/100 g, but fried, the content is reduced to 2.7 mg/100 g. Chicken eggs contain no vitamin C, raw or cooked. Vitamin C is present in human breast milk at 5.0 mg/100 g and 6.1 mg/100 g in one tested sample of infant formula, but cow's milk contains only 1.0 mg/100 grams. Plant sources. Vitamin C chemically decomposes under certain conditions, many of which may occur during the cooking of food. Vitamin C concentrations in various food substances decrease with time in proportion to the temperature at which they are stored, and cooking can reduce the vitamin C content of vegetables by around 60%, possibly partly due to increased enzymatic destruction, as it may be more significant at sub-boiling temperatures. Longer cooking times also add to this effect, as will copper food vessels, which catalyze the decomposition. Another cause of vitamin C being lost from food is leaching, where the water-soluble vitamin dissolves into the cooking water, which is later poured away and not consumed. However, vitamin C does not leach in all vegetables at the same rate. Research shows broccoli seems to retain more than any other. Research has also shown that freshly cut fruits do not lose significant nutrients when stored in the refrigerator for a few days. Vitamin C dietary supplements are available as tablets, capsules, drink mix packets, in multivitamin/mineral formulations, in antioxidant formulations, and as crystalline powder. Vitamin C is also added to some fruit juices and juice drinks. Tablet and capsule content ranges from 25 mg to 1,500 mg per serving. The most commonly used supplement compounds are ascorbic acid, sodium ascorbate, and calcium ascorbate. Vitamin C molecules can also be bound to the fatty acid palmitate, creating ascorbyl palmitate, or else incorporated into liposomes. Animal sources. Food preparation. Supplements. In 2014, the Canadian Food Inspection Agency evaluated the effect of fortification of foods with ascorbate in the guidance document, Foods to which vitamins, mineral nutrients, and amino acids may or must be added. Voluntary and mandatory fortification was described for various classes of foods. Among foods classified for mandatory fortification with vitamin C were fruit-flavored drinks, mixes, and concentrates, foods for a low-energy diet, meal replacement products, and evaporated milk. From the U.S. National Institutes of Health, approximately 70–90% of vitamin C is absorbed at moderate intakes of 3180 mg/day. However, at doses above 1000 mg/day, absorption falls to less than 50%. Ascorbic acid is absorbed in the body by both active transport and simple diffusion. Sodium-dependent active transport sodium ascorbate CO transporters and hexose transporters are the two transporter proteins required for active absorption. SVCT1 and SVCT2 import the reduced form of ascorbate across plasma membranes. GLUT1 and GLUT3 are glucose transporters, and transfer only the dehydroascorbic acid form of vitamin C. Although dehydroascorbic acid is absorbed in higher rate than ascorbate, the amount of dehydroascorbic acid found in plasma and tissues under normal conditions is low, as cells rapidly reduce dehydroascorbic acid to ascorbate. SVCTs appear to be the predominant system for vitamin C transport in the body, the notable exception being red blood cells, which lose SVCT proteins during maturation. In both vitamin C synthesizers and non-synthesizers, cells with few exceptions maintain ascorbic acid concentrations much higher than the approximately 50 micromoles/liter found in plasma. For example, the ascorbic acid content of pituitary and adrenal glands can exceed 2000 moles/L, and muscle is at 200 to 300 moles/L. The known coenzymatic functions of ascorbic acid do not require such high concentrations, so there may be other, as yet unknown functions. Consequences of all this organ content is that plasma vitamin C is not a good indicator of whole body status, and people may vary in the amount of time needed to show symptoms of deficiency when consuming a diet very low in vitamin C. Excretion can be as ascorbic acid, via urine. In humans, during times of low dietary intake, vitamin C is reabsorbed by the kidneys rather than excreted. Only when plasma concentrations are 1.4 mg/dl or higher does reabsorption decline and the excess amounts pass freely into the urine. This salvage process delays onset of deficiency. Ascorbic acid also converts to dehydroascorbate and from that compound non-reversibly to 2,3-dictagluonate and then oxalate. These three compounds are also excreted via urine. Humans are better than guinea pigs at converting DHA back to ascorbate, and thus take much longer to become vitamin C deficient. Food fortification. Ascorbic acid performs numerous physiological functions in the human body. These functions include the synthesis of collagen, carnitine, and neurotransmitters, the synthesis and catabolism of tyrosine, and the metabolism of microsome. During biosynthesis, ascorbate acts as a reducing agent, donating electrons and preventing oxidation to keep iron and copper atoms in their reduced states. Vitamin C acts as an electron donor for 8 enzymes. The name vitamin C always refers to the L-enantiomer of ascorbic acid and its oxidized forms, such as dehydroascorbate. Therefore, unless written otherwise, ascorbate and ascorbic acid refer in the nutritional literature to L-ascorbate and L-ascorbic acid respectively. Ascorbic acid is a weak sugar acid structurally related to glucose. In biological systems, ascorbic acid can be found only at low pH, but in solutions above pH 5 is predominantly found in the ionized form, ascorbate. All of these molecules have vitamin C activity and thus are used synonymously with vitamin C, unless otherwise specified. Numerous analytical methods have been developed for ascorbic acid detection. For example, vitamin C content of a food sample such as fruit juice can be calculated by measuring the volume of the sample required to decolorize a solution of dichlorophenolenediphenol and then calibrating the results by comparison with a known concentration of vitamin C. Simple tests are available to measure the levels of vitamin C in the urine and in serum or blood plasma. However, these reflect recent dietary intake rather than total body content. It has been observed that while serum or blood plasma concentrations follow a circadian rhythm or reflect short-term dietary impact, content within tissues is more stable and can give a better view of the availability of ascorbate within the entire organism. However, very few hospital laboratories are adequately equipped and trained to carry out such detailed analyses. The vast majority of animals and plants are able to synthesize vitamin C, through a sequence of enzyme-driven steps, which convert monosaccharides to vitamin C. In plants, this is accomplished through the conversion of mannose or galactose to ascorbic acid. In some animals, glucose needed to produce ascorbate in the liver is extracted from glycogen. Ascorbate synthesis is a glycogenolysis-dependent process. Among the mammals that have lost the ability to synthesize vitamin C are simians and tarsias, which together make up one of two major primate suborders, Haplorini. This group includes humans. The other more primitive primates have the ability to make vitamin C. Synthesis does not occur in a number of species in the small rodent family Caeiidae that includes guinea pigs and capybaras, but occurs in other rodents. In reptiles and birds, the biosynthesis is carried out in the kidneys. A number of species of passerine birds also do not synthesize, but not all of them, and those that do not are not clearly related. There is a theory that the ability was lost separately a number of times in birds. In particular, the ability to synthesize vitamin C is presumed to have been lost and then later reacquired in at least 2 cases. The ability to synthesize vitamin C has also been lost in about 96% of fish. Most tested families of bats, including major insect and fruit-eating bat families, cannot synthesize vitamin C. A trace of guanylactone oxidase was detected in only one of 34 bat species tested, across the range of 6 families of bats tested. There are at least 2 species of bats, frugivorous bat and insectivorous bat, that retain their ability of vitamin C production. These animals all lack the L-guanylactone oxidase enzyme, which is required in the last step of vitamin C synthesis. The genomes of these species contain GULOS pseudogenes, which serve as insight into the evolutionary past of the species. Mechanism of action: absorption, transport, and excretion. Some of these species are able to make do with the lower levels available from their diets by recycling oxidized vitamin C. Most simians consume the vitamin in amounts 10 to 20 times higher than that recommended by governments for humans. This discrepancy constitutes much of the basis of the controversy on current recommended dietary allowances. It is countered by arguments that humans are very good at conserving dietary vitamin C, and are able to maintain blood levels of vitamin C comparable with simians on a far smaller dietary intake, perhaps by recycling oxidized vitamin C. Enzymatic cofactor. In vertebrates that can synthesize ascorbic acid, the biosynthesis pathway starts with glucose, either taking place in the liver for mammals and some birds, or the kidneys for amphibians, reptiles, and some birds. The pathway is the same. Several enzymes catalyze steps from D-glucose to D-glucuronate. Next, the enzyme glucuronate reductase converts D-glucuronate to L-gluconate. Then the enzyme guanylactonase converts L-gluconate to L-guanylactone. The final enzymatic conversion is by the enzyme L-guanylactone oxidase, to 2-keto-guanylactone. From this compound, the last step is a spontaneous, i.e., non-enzymatic conversion to ascorbic acid. GLO is the enzyme that is absent in animal species unable to synthesize vitamin C. Chemistry. Testing 4 levels. Synthesis, biosynthesis, roots, evolution, industrial, history, folk medicine, scurvy at sea, discovery, large doses, society and culture. Notes: all plants synthesize ascorbic acid. Ascorbic acid functions as a cofactor for enzymes involved in photosynthesis, synthesis of plant hormones, as an antioxidant and also regenerator of other antioxidants. Plants use multiple pathways to synthesize vitamin C. The major pathway starts with glucose, fructose, or mannose and proceeds to L-galactose, L-gluconolactone and ascorbic acid. There is feedback regulation in place, in that the presence of ascorbic acid suppresses enzymes in the synthesis pathway. This process follows a diurnal rhythm, so that enzyme expression peaks in the morning to support biosynthesis later on when midday sunlight intensity demands high ascorbic acid concentrations. Minor pathways may be specific to certain parts of plants. These can be either identical to the vertebrate pathway, or start with inositol and get to ascorbic acid via L-galactonic acid to L-galactonolactone. Ascorbic acid is a common enzymatic cofactor in mammals used in the synthesis of collagen, as well as a powerful reducing agent capable of rapidly scavenging a number of reactive oxygen species. Given that ascorbate has these important functions, it is surprising that the ability to synthesize this molecule has not always been conserved. In fact, anthropoid primates, Cavia porcellus, teleost fishes, most bats, and some passeriform birds have all independently lost the ability to internally synthesize vitamin C in either the kidney or the liver. In all of the cases where genomic analysis was done on an ascorbic acid auxotroph, the origin of the change was found to be a result of loss-of-function mutations in the gene that codes for L-gulinogamma-lactone oxidase, the enzyme that catalyzes the last step of the ascorbic acid pathway outlined above. In the case of the simians, it is thought that the loss of the ability to make vitamin C may have occurred much farther back in evolutionary history than the emergence of humans or even apes, since it evidently occurred soon after the appearance of the first primates, yet some time after the split of early primates into the two major suborders Haplorini and its sister suborder of non-Tarsia prosimians, the Strepsirini, which retained the ability to make vitamin C. According to molecular clock dating, these two suborder primate branches parted ways about 63 to 60 million years ago. Approximately 3 to 5 million years later, only a short time afterward from an evolutionary perspective, the infra-order Tarsiiformes, whose only remaining family is that of the Tarsia, branched off from the other haplorhines. Since Tarsias also cannot make vitamin C, this implies the mutation had already occurred, and thus must have occurred between these two marker points. One explanation for the repeated loss of the ability to synthesize vitamin C is that it was the result of genetic drift. Assuming that the diet was rich in vitamin C, natural selection would not act to preserve it. Some scientists have suggested that loss of the vitamin C biosynthesis pathway may have played a role in rapid evolutionary changes, leading to hominids and the emergence of human beings. According to this theory, the loss of ascorbic acid's antioxidizing properties would have led to an increase in free radicals in the body. Free radicals are known to increase the frequency of genetic mutations, which would subsequently increase the speed of evolution. It has also been noted that the loss of the ability to synthesize ascorbate strikingly parallels the inability to break down uric acid, also a characteristic of primates. Uric acid and ascorbate are both strong reducing agents. This has led to the suggestion that, in higher primates, uric acid has taken over some of the functions of ascorbate. Vitamin C is produced from glucose by two main routes. The Reichstein process, developed in the 1930s, uses a single pre-fermentation followed by a purely chemical route. The modern two-step fermentation process, originally developed in China in the 1960s, uses additional fermentation to replace part of the later chemical stages. Both processes yield approximately 60% vitamin C from the glucose feed. World production of synthesized vitamin C was estimated at approximately 110,000 tons annually in 2000. Traditionally, the main producers were BASF/Takeda, DSM, Merck, and the China Pharmaceutical Group Limited of the People's Republic of China. By 2008 only the DSM plant in Scotland remained operational outside of China because of the strong price competition from China. The world price of vitamin C rose sharply in 2008, partly as a result of rises in basic food prices but also in anticipation of a stoppage of the two Chinese plants, situated at Shijiazhuang near Beijing, as part of a general shutdown of polluting industry in China over the period of the Olympic Games. Production resumed after the Olympics, but then 5 Chinese manufacturers met in 2010, among them Northeast Pharmaceutical Group and North China Pharmaceutical Group, and agreed to temporarily stop production in order to maintain prices. In 2011, an American suit was filed against 4 Chinese companies that allegedly colluded to limit production and fix prices of vitamin C in the United States. The companies did not deny the accusation but say in their defense that the Chinese government compelled them to act in this way. In January 2012, a United States judge ruled that the Chinese companies can be sued in the U.S. by buyers acting as a group. A verdict was reached in March 2013 imposing a $147.8 million fine. This verdict was reversed by the Second U.S. Circuit Court of Appeals in New York, on the grounds that China formally advised the court that its laws required the vitamin C makers to violate the Sherman Act, a U.S. antitrust law. In June 2017, the U.S. Supreme Court announced that it would consider an appeal filed to reverse the lower court decision. The need to include fresh plant food or raw animal flesh in the diet to prevent disease was known from ancient times. Native people living in marginal areas incorporated this into their medicinal lore. For example, spruce needles were used in temperate zones in infusions, or the leaves from species of drought-resistant trees in desert areas. In 1536, the French explorers Jacques Cartier and Daniel Nazevik, exploring the St. Lawrence River, used the local natives' knowledge to save his men who were dying of scurvy. He boiled the needles of the arbor vitae tree to make a tea that was later shown to contain 50 mg of vitamin C per 100 grams. In the 1497 expedition of Vasco da Gama, the curative effects of citrus fruit were known. The Portuguese planted fruit trees and vegetables in St. Helena, a stopping point for homebound voyages from Asia, and left their sick to be taken home by the next ship. Authorities occasionally recommended plant food to prevent scurvy during long sea voyages. John Woodall, the first surgeon to the British East India Company, recommended the preventive and curative use of lemon juice in his 1617 book, The Surgeon's Mate. In 1734, the Dutch writer Johann Bachstrom gave the firm opinion that scurvy is solely owing to a total abstinence from fresh vegetable food, and greens. Scurvy had long been a principal killer of sailors during the long sea voyages. According to Jonathan Lamb, in 1499, Vasco da Gama lost 116 of his crew of 170, in 1520, Magellan lost 208 out of 230, all mainly to scurvy. The first attempt to give scientific basis for the cause of this disease was by a ship's surgeon in the Royal Navy, James Lind. While at sea in May 1747, Lind provided some crew members with 2 oranges and 1 lemon per day, in addition to normal rations, while others continued on cider, vinegar, sulfuric acid, or sea water, along with their normal rations, in one of the world's first controlled experiments. The results showed that citrus fruits prevented the disease. Lind published his work in 1753 in his treatise on the scurvy. Fresh fruit was expensive to keep on board, whereas boiling it down to juice allowed easy storage but destroyed the vitamin. It was 1796 before the British Navy adopted lemon juice as standard issue at sea. In 1845, ships in the West Indies were provided with lime juice instead, and in 1860 lime juice was used throughout the Royal Navy, giving rise to the American use of the nickname limey for the British. Captain James Cook had previously demonstrated the advantages of carrying sauerkraut on board, by taking his cruise to the Hawaiian Islands without losing any of his men to scurvy. For this, the British Admiralty awarded him a medal. The name antiscorbutic was used in the 18th and 19th centuries for foods known to prevent scurvy. These foods included lemons, limes, oranges, sauerkraut, cabbage, malt, and portable soup. In 1928, the Canadian Arctic anthropologist Vilhjalmur Stephenson showed that the Inuit avoid scurvy on a diet of largely raw meat. Later studies on traditional food diets of the Yukon First Nations, Dene, Inuit, and Métis of northern Canada showed that their daily intake of vitamin C averaged between 52 and 62 mg/day, comparable with the estimated average requirement. Vitamin C was discovered in 1912, isolated in 1928 and synthesized in 1933. Making it the first vitamin to be synthesized. Shortly thereafter Thaddeus Reichstein succeeded in synthesizing the vitamin in bulk by what is now called the Reichstein process. This made possible the inexpensive mass production of vitamin C. In 1934 Hoffmann-La Roche trademarked synthetic vitamin C under the brand name Redoxon and began to market it as a dietary supplement. In 1907 a laboratory animal model which would help to identify the antiscorbutic factor was discovered by the Norwegian physicians Axel Holst and Theodor Froelich, who when studying shipboard beriberi, fed guinea pigs their test diet of grains and flour and were surprised when scurvy resulted instead of beriberi. By luck, this species did not make its own vitamin C, whereas mice and rats do. In 1912, the Polish biochemist Casimir Funk developed the concept of vitamins. One of these was thought to be the antiscorbutic factor. In 1928, this was referred to as water-soluble C, although its chemical structure had not been determined. From 1928 to 1932, Albert Szent-Györgyi and Joseph L. Sverbely's Hungarian team, and Charles Glenn King's American team, identified the antiscorbutic factor. Szent-Györgyi isolated hexuronic acid from animal adrenal glands, and suspected it to be the antiscorbutic factor. In late 1931, Szent-Györgyi gave Sverbely the last of his adrenal-derived hexuronic acid with the suggestion that it might be the antiscorbutic factor. By the spring of 1932, King's laboratory had proven this, but published the result without giving Szent-Györgyi credit for it. This led to a bitter dispute over priority. In 1933, Walter Norman Hayworth chemically identified the vitamin as L-hexuronic acid, proving this by synthesis in 1933. Hayworth and Szent-Györgyi proposed that L-hexuronic acid be named ascorbic acid, and chemically L-ascorbic acid, in honor of its activity against scurvy. The term's etymology is from Latin, a meaning away, or off from, while scorbic is from medieval Latin scorbuticus, cognate with Old Norse skerbjugr, French skorbut, Dutch skerbic and Low German scharbach. Partly for this discovery, Szent-Györgyi was awarded the 1937 Nobel Prize in Medicine, and Hayworth shared that year's Nobel Prize in Chemistry. In 1957, J.J. Burns showed that some mammals are susceptible to scurvy as their liver does not produce the enzyme L-guanylactone oxidase, the last of the chain of 4 enzymes that synthesize vitamin C. American biochemist Irwin Stone was the first to exploit vitamin C for its food preservative properties. He later developed the theory that humans possess a mutated form of the L-guanylactone oxidase coding gene. In 2008, researchers at the University of Montpellier discovered that in humans and other primates the red blood cells have evolved a mechanism to more efficiently utilize the vitamin C present in the body by recycling oxidized L-dehydroascorbic acid back into ascorbic acid for reuse by the body. The mechanism was not found to be present in mammals that synthesize their own vitamin C. Vitamin C megadosage is a term describing the consumption or injection of vitamin C in doses comparable to or higher than the amounts produced by the livers of mammals which are able to synthesize vitamin C. The theory behind this, although not the actual term, was described in 1970 in an article by Linus Pauling, a famous scientist who had been awarded the Nobel Prize in Chemistry in 1954. Briefly, his position was that for optimal health, humans should be consuming at least 2,300 mg/day to compensate for the inability to synthesize vitamin C. The recommendation also fell into the consumption range for gorillas, a non-synthesizing near relative to humans. A second argument for high intake is that serum ascorbic acid concentrations increase as intake increases until it plateaus at about 190 to 200 micromoles per liter once consumption exceeds 1,250 milligrams. As noted, government recommendations are a range of 40 to 110 mg/day and normal plasma is approximately 50 moles/L. So normal is about 25% of what can be achieved when oral consumption is in the proposed megadose range. Linus Pauling, famous awardee of the Nobel Prize for Chemistry, popularized the concept of high-dose vitamin C as prevention and treatment of the common cold in 1970. A few years later he proposed that vitamin C would prevent cardiovascular disease, and that 10 grams/day, initially administered intravenously and thereafter orally, would cure late-stage cancer. Megadosing with ascorbic acid has other champions, among them chemist Irwin Stone and the controversial Matthias Rath and Patrick Halford, who both have been accused of making unsubstantiated treatment claims for treating cancer and HIV infection. The megadosing theory is to a large degree discredited. Modest benefits are demonstrated for the common cold. Benefits are not superior when supplement intakes of more than 1,000 mg/day are compared to intakes between 200 and 1,000 mg/day, and so not limited to the megadose range. The theory that large amounts of intravenous ascorbic acid can be used to treat late-stage cancer is, some 40 years after Pauling's seminal paper, still considered unproven and still in need of high-quality research. However, a lack of conclusive evidence has not stopped individual physicians from prescribing intravenous ascorbic acid to thousands of people with cancer. In February 2011, the Swiss Post issued a postage stamp bearing a depiction of a model of a molecule of vitamin C to mark the International Year of Chemistry.